Hello, my people. I hope we're doing well. This is the fourth and final video for the integration by parts. In the first two videos, I sort of introduced it and did some examples using indefinite integrals. The third video, the last video, was definite integrals. And on this one, I'm going to show you briefly when you're given something that requires multiple iterations of the integration by parts, you actually can set it up in a table, and that's kind of nice. Okay. Now we already seen that x e to the x dx is equal to this, and we saw that when we saw that in class. So we have u in this one equal to e to the x, and du is going to be 2x dx. And this basically is the same as this, but we know we're going to have to do it twice because it's going to take two iterations of differentiation to get x squared down to a constant, okay? So we have dv is e to the x dx, and v is equal to e to the x. And when we put it together, we get, x squared e to the x minus 2 x e to the x dx. Now, we're going to use this up here to speed things along, but we would have to basically do this process again, but in this case we're not going to. And so we have negative 2 x e to the x minus e to the x plus c. And the only reason I don't include the c in here is that when you distribute a negative 2 to some random constant, it just still is a random constant. So when you multiply c by a constant, it just doesn't affect it. Plus 2 e to the x plus c. Okay, well, let's say we were given, x cubed e to the x, and you would do the same thing. You would, x cubed, and du is 3x squared dx, and our dv is equal to e to the x dx, and e to the x, and oh my gosh, this is getting exhausting. And you say, okay, well, uv, x cubed e to the x minus 3 times the integral of x squared e to the x dx. Well, I happen to have this integral right up here, so we'll plug it in just to save time. And you get negative 3 times x squared e to the x minus 2x e to the x plus 2 e to the x plus c. And that winds up being x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. And, on all of these, if you want to clean it up a little bit, you can factor out an e to the x and get x cubed minus 3x squared plus 6x minus 6 plus c. And if you'll notice, each successive term is the negative of the derivative of the preceding term. Well, that shouldn't surprise anybody. So if we actually, instead of having to do the x e to the x and the x squared e to the x and the x cubed e to the x and having to do 3 rounds of it, there actually is a way to sort of consolidate that work into a table. Now, of course, you'll have to draw the table yourself. I just wanted to make it nice and tidy for being able to present it to you. What we want to do is each round, notice that basically the terms here and the terms here are the u times v, right? Each term right here is the uv of each round. And so basically what we really need is we need a table that will spit out our u times v values. But remember that every time you're doing this, you are distributing this negative across, right? Distributing this negative across. And so by necessity, the sign will flip-flop positive, negative, positive, negative. So what we did is we just plopped e to the x in here and x cubed in here. But because this is dv and this is u, we need to actually do 1 round of anti-differentiation to have uv. Okay, that's why these two blocks are sort of shaded out. And this becomes 3x squared. So under u, you just take the derivative of each round. And under dv, you take the antiderivative. Now, for e to the x, it winds up being really, really simple. And you know you're done once you get down here to 0, because that's going to make that term a non-event. And basically, it's positive x cubed e to the x, negative 3x squared e to the x, positive 6x e to the x, minus 6 e to the x plus c. And gee whiz, that looks exactly like that. And so the tabular method, if you know, you keep things nice and tidy and you set it up correctly, winds up making multi-step integration by parts actually quite easy on occasion. So let's go ahead and do another example. Okay, now this one, obviously, I need the t right here, and the dv is going to be sine of 2t. Now this one isn't e to the x, so it's actually going to be a little bit difficult. I just have to be careful about anti-differentiating. Sine 2t is the derivative of what? Well, sine is the derivative of negative cosine, but of course I have to take into account the angle measurement right here, so negative 1/2 cosine of 2t. And then basically in the middle column, the t cubed, I need to go ahead and differentiate all the way down. And then of course when I get to here, I realize that I'm done. Here I need to anti-differentiate, so the derivative of cosine is the derivative of sine, so its antiderivative is positive sine, so the negative persists, and I need another 1/2 out in front here for that angle measurement expression. And then of course sine, the sine is the derivative of negative cosine, so its antiderivative is negative cosine, turning this to a positive 1/8 cosine 2t. And then, you know, and once you get into here, you can see the pattern. It's like, you know, positive, you know, negative, negative, positive, positive, negative, negative, positive, positive, negative. And of course, this becomes 1/2, 1/4, 1/8, 1/16. And so there's a pattern there, obviously, that can be observed. And now, from here, it's just these 4 rows. So it's negative t cubed, or negative 1/2 t cubed cosine 2t, positive 3/4 t squared sine 2t, positive 3/4 t cosine 2t, and it's 3/4 because, you know, 6/8 reduced, and then negative 3/8 sine 2t plus c. And that's it. And, you know, if you wanted to, you could clean this up a little bit and combine the cosine 2t with the cosine 2t. So you could do something weird like, or not weird, but, you know, something like, you know, t over 2 cosine 2t. And, you know, what's left is 3/2 minus t squared. And then you could basically factor out from both of the sine 2t's 3/4 sine of 2t, and what's left is, you know, t squared minus 1/2 plus c, just to make it, you know, if you want to make it look more aesthetically pleasing or whatever. But basically each time you do this, you're getting the next round of uv, and then you're just changing sign, because the sign will change necessarily, because each time you're distributing that negative across, and that will make it sort of flip-flop between positive, negative, positive, negative. And that's it. That's really, there's really not much to it. It's a really nice way of keeping things organized when you're dealing with integration by parts that needs to be done in several successive iterations. But as always, you know, if you have any questions, please do shoot me an email. I hope this has been helpful. Between these videos and the old ones that I've posted here in the same playlist, I'm hoping that this will be sufficient. We'll go over it on Wednesday before we launch into the next section, which is trigonometric integrals. So, bye guys.